Centripetal acceleration. You may have noticed this word at the very beginning, centripetal. So let's take a look at what this word actually means. So what's it mean? Well, a quick Google search will pop up. It means moving or tending to move toward a center. So when we talk about centripetal acceleration, what do we mean? We mean acceleration towards the center of a circular path or circular arc. It doesn't have to be a full circle, it just has to be a part of it that looks curved. It might be useful to talk about the magnitude of centripetal acceleration if we're going to be using it. So we have a circle, and you're going around the circle at a constant speed, which is the magnitude of velocity. Now remember, velocity includes direction, so your velocity is changing, but your speed's going to be the same. The length of these arrows is going to be the same. Also notice that your velocity is tangential to the circle, which means 90 degrees. Which means, if I move those velocity vectors to make a triangle, I put v1 over here, v2 right here, the angle between your velocity vectors is the angle between your radius vectors. Now that's pretty cool. So wait, I've got r equals r, v equals v. I have two isosceles triangles that have the same angle in the middle, which means I can set up similar triangles. The ratio of change in velocity over velocity is the same as the ratio of the change in radius, change in the radial vector, the change in your position, to r. Okay, so that's good. Let's do this. Let's multiply both sides by v. That goes over there. But I'm interested in acceleration, so I'm going to look at how this changes with time. So dv dt, delta v over delta t, that gives you acceleration on this side. Wait a minute, delta r over t, that looks familiar. That's velocity. So the magnitude of your centripetal acceleration is equal to your tangential velocity over r. Oh yeah, that's cool. And again, it's centripetal acceleration, which means towards the center. Last time we talked about this, which was a minute and a half ago, we used pictures. Now let's use math. There's also a great way of looking through in your textbook, so if this is a little fast, I would recommend getting your textbook, opening it up, having it in front of you while we do this. So we'll break this up into, we want velocity. So we're going to look at the difference in position. So r hat is your position vector. Well, it's actually the position unit vector, which is why it has the magnitude r. So we're going to look at how that r hat changes. So we know x is related to cosine, y is related to sine. We take the derivatives. Now I have negative sine and cosine with d theta dt. Well, that's omega. Okay, great. That's cool. That's cool. We still want acceleration. But what we have here is that this is the tangential direction, tangential to a circle. All right. So now let's take the derivative of this with respect to that tangent vector. We split it up because you can look at how omega changes with time. Oh, wait. And this is in the tangential direction. So this would be like you speed up or slow down. Speed, we'll just say changes with this one. And over here, this is just a directional. But if you look at this magnitude looks like it's going to stay the same. It's just going to be some tangential change in direction. So we look at this, take the couple derivatives through the magic of math, which please follow the steps as we take this derivative. Oh wait, cosine x, sine y, well that's just r hat, which is the distance away from the center, the direction away from the center. Oh, but you still have these negatives. So this whole term is just negative r hat, which means you can speed up or slow down on the edge of the circle. You go faster or slower. And you're also turning toward the center of the circle. Pretty neat. So we just added this new direction called the centripetal direction. So a centripetal force is just force directed towards the center. It is not a new force. It is an old force. When you see centripetal, it's just a direction. Right? So don't think of it centripetal as any different than x or y. Let's work a couple examples. We've got a flatbed truck going around a circle. There's a tree in this flatbed truck. All right. Coefficient of static friction, because you don't want that tree to fall out of your truck. How fast can you go around the curve? Well, let's draw a force diagram on this tree. I've got normal force mg, and then, oh look, this would be towards the center direction. So we'll start with the y direction, which is familiar. Are you accelerating the y direction? Well, no. All right. So you get your normal force is equal to mg. Well, that's useful because that relates to this force of friction. Here are the changes. Now I'm interested in the centripetal direction, towards the center. So what force goes towards the center? Well, friction goes towards the center, USN. And then I substituted my magnitude for centripetal acceleration because I already know it's going towards the center. All right. And now it's just math. So solve for that tangential velocity. The m's go away. And so n over m. Now you're left with just USRG. All right, so same way we used problems before, except now we just add this centripetal direction towards the center of a circle. Now we're going to try a little bit different approach. And this actually uses a combination of approaches. So this block's going to go, ooh, and it's going to go over here. And if you've ever gone over a hill too fast or on a roller coaster, you feel your stomach kind of go around, that means your apparent weight goes down. Oh. And if you're going too fast, you would actually lose connections with the track. So at some point, roller coasters have little wheels underneath that hold onto the track to prevent that from happening. So let's look at the top of the hill. At the top of the hill, in this case, the center direction is down. So that'll be my c hat, towards the center of curvature. So n minus mg is mac. Oh, okay, so n is 0. And the reason it's 0, because when we're at the top of the hill, this is the minimum normal force, right? So before you fly off, your normal force that you're going to feel is 0. So we plugged in that condition. And your m's go away, and you just get that your centripetal acceleration is equal to g. Okay, good. But we want to relate this to our tangential velocity. So g is v squared over r. And if you're taking long, this would just be vt equals square root of gr. That's good. But you need to find that velocity. Now this looks like a job for energy conservation because I start up here. I'm going to go. So let's look at this. No springs, nothing's rotating. Oh, do I have any kinetic energy at the beginning? Well, no. No kinetic energy at the beginning. Do I have any gravitational potential energy at the beginning? Yeah, because you're up here and at the end. All right, so we got to keep those two terms. 1/2 mv squared. This is at the hill. This distance was r, so at the end you have mgr for your potential energy. At the beginning you have mgh, and we are solving for h. But remember, we got your velocity, the max velocity you can have is gr, square root of gr. So square root of gr squared gives you gr. Now it's just a matter of mathing it out. Oh look, mass goes away. What does this mean? This means it could be an elephant, it could be a mouse. Doesn't matter. Same ratio with the size of hills. All right. Oh, look, there was a g in all of those terms, too. Well, this makes things nice. And you get h is equal to 3/2 r. That's the maximum top of the hill. So in this case, we looked at the centripetal direction on the hill, and then we used conservation of energy. So once we knew how fast we could go from our centripetal force equations and relating AC, your centripetal acceleration, is v squared over r. That's the magnitude. Then we use conservation of energy to find that v and the height of this hill. All right, I hope that helps. Please ask lots of questions. I will see you in class.